Hello everyone, welcome back to this series on solutions to previous year GATE chemical reaction engineering questions. In the part 4 of this series, we will be looking at the questions from GATE 2022. So let's move on to the first question. The reaction A giving B is carried out isothermally on a porous catalyst. The intrinsic reaction rate is KCA square, where K is the rate constant and Ca is the concentration of A. If the reaction is strongly pore diffusion controlled, the observed order of the reaction is. So this is a pretty straightforward question relating to strong pore diffusion controlled reactions. So when it comes to strong pore diffusion controlled reactions, there are two typical observations that are made. So one pertaining to the order of the reaction, where the observed order of the reaction will become n plus 1 by 2. And the other other common observation is the observed activation energy will be half of the true activation energy. So in this reaction, it is given that the order is second order. So hence the observed order will be n plus 1 by 2, that is 2 plus 1 by 2, which is 3 by 2. Hence the right option to this question is option C. Let's move on to the next question. In an enzymatic reaction, an inhibitor I competes with the substrate S to bind with the enzyme E, thereby reducing the rate of product P formation. The competitive inhibition follows the reaction mechanism shown below. Assuming pseudo steady state approximation, we need to find the correct plot of 1 by minus Rs versus 1 by concentration of S. So let's see the solution to this question. Since pseudo steady state approximation can be used, so for the given equilibrium reactions, we can write the equilibrium constants as follows. For the first reaction, the equilibrium constant capital K will be a ratio of small k1 and k2, which is equal to concentration of E dot S divided by product of the concentrations of E and S. Similarly, for the second equilibrium reaction, the equilibrium constant capital Ki will be the ratio of small ki and small k minus I, which is equal to the ratio of concentration of E dot I with the product of the concentrations of E and I. Now, we can also say that the total concentration of E is constant. That is, the concentration of empty enzyme sites, the constant plus the concentration of the enzyme sites bound to the substrate, plus the concentration of enzyme sites bound to the inhibitor will be equal to a constant, which is same. Now, from the deduced expressions for equilibrium constants, we can write CES and CEI in terms of CE and CE, CS and CI. So C naught will be CE plus capital K CE CS plus Ki CE Ci. Further, we can take CE common in the RHS and deduce an expression for CE. CE will be equal to C naught by 1 plus KCS plus Ki Ci. So let this be equation 1. So from the overall stoichiometry, we can write that the rate of consumption of S, that is minus Rs, will be equal to rate of formation of P, that is Rp. Now from the given mechanism, we can write Rp as K3 into CES. So from the equilibrium constant that was reduced earlier, we can write CES as capital K CE into CS. Further, from equation 1, we can write the rate expression as minus Rs will be equal to K3 capital K C naught CS divided by 1 plus capital K CS plus capital Ki Ci. So we can take capital K common from numerator and denominator and cancel. And further, we will have to take the reciprocal of the parameters present on both the sides of this expression, because we need to find the plot of 1 by minus Rs versus 1 by concentration of S. Here it is CS. So on taking the reciprocal on both sides, we get 1 by minus Rs is equal to 1 plus Ki Ci by K, K3 C naught into 1 by Cs plus 1 by K3 C naught. So this is an equation of straight line. So if we observe this equation of straight line, we can say that y-intercept is unaffected by the concentration of inhibitor because there is no presence of the term Ci, whereas only slope is impacted by the presence of inhibitor because of presence of Ci. So hence y-intercept is unaffected by Ci. So in the given options, we need to find a plot where the presence of inhibitor do not change the y-intercept. Now, if we observe the plots given in options B, C, and D, clearly with the increase in concentration of I, the y-intercept is changing in all these three plots. However, in plot A, the y-intercept remains unchanged. So hence, option A is the correct option to this question, which shows the plot of 1 by minus Rs versus 1 by concentration of S. So hence, this is an important point to remember. The presence of inhibitor in competitive inhibition do not impact the y-intercept of the straight line equation of 1 by minus Rs versus 1 by concentration of S. So typically these kinds of plots, which is basically the 1 by rate versus the concentration plots, is referred to as Lineweaver-Burke plots. So hence, if a student is aware of the behaviors of these Lineweaver-Burke plots for various inhibitions, namely competitive, uncompetitive, and non-competitive inhibitions, we can directly choose the correct plot given in the options. So with that being said, let's move on to the next question. An elementary irreversible liquid phase reaction 2A giving B is carried out under isothermal conditions in a 1 meter cube ideal plug flow reactor. The volumetric flow rate of fresh A is 10 meter cube per hour and the concentration is 2 kilomole per meter cube. So there is a recycle stream that is introduced. When the recycle ratio is 0, the conversion of A at the location 2 with respect to fresh feed at location 1 is 50%. When R is tending to infinity, what will be the conversion of A? So let's see the solution to this question. So the reaction is 2A giving B and it is elementary. So hence the order will be 2. We know the volume of the PFR and the rate constant of this reaction is not given. So let's analyze the two cases that are given. And the first case is when R is equal to 0. So we know that when R is equal to 0, the recycle reactor behaves like an ideal PFR. So let's write the design equation for the ideal PFR. Tau by Ca naught is equal to 0 to integral 0 to Xa dxa by minus Ra. So for the second order reaction given, minus Ra will be Kca square, which is equal to K times Ca1 into 1 minus Xa whole square. So Ca1 is the initial concentration as per the given diagram. So further we can write tau as capital V by small v1 and Ca naught is Ca1 as per the diagram. And we are integrating from 0 to 0.5 because conversion is given as 50%. So on further substituting the values of the parameters given, we can write this expression as 1 by 10 is equal to 1 by K Ca1 integral 0 to 0.5 dxa by 1 minus Xa whole square. So we can integrate this expression and substitute the values of Ca1 and find the value of K as 5 meter cube per mole second. Let's analyze the second scenario. When R is equal to infinity, the recycle reactor behaves like an ideal CSTR. So let's write the design equation for the ideal CSTR. Tau by Ca naught is Xa by minus Ra. So further we can write this as V by V1 into Ca1 is equal to Xa by Kca1 into 1 minus Xa whole square. So we can cancel out one of the Ca1s, substitute all the parameters and retain Xa in the RHS. So it will be Xa by 1 minus Xa whole square is equal to 1. So further simplification will give us a quadratic in Xa. Xa square minus 3Xa plus 1 equal to 0. So the roots of this quadratic equation will be 0.382 and 2.618. So 2.618 is impractical. Conversion cannot be more, XA cannot be more than 1. So hence the right answer to the conversion will be 0.382. So in terms of percentage, the conversion will be 38.2%. So hence the right solution to this question is 38.2. So with that, we come to the end of part 4 of this series. So in this part, we looked at some of the questions from GATE 2022 pertaining to clinical reaction engineering. In part 5, we will complete the remaining questions from GATE 2022. So I hope you like this video. Please share and subscribe to this channel. And we will see you in the next part. Thank you.